Okay, so welcome everyone. I am Soumya Vemuri and I'm today's event moderator. Thank you for joining today's session, Demystifying 5G Security Through Threat Modeling. Please welcome our amazing speaker, Suhuna Thiruppathi. Suhuna is an engineering leader with ample industry experience across various technology and management domains such as 3G, 4G, 5G, SDN, NVF, VNF, Kubernetes, RAN, networking, as well as innovation leadership, solution engineering, and team building. Thank you, Suhuna, for being here today. I will now pass the session over to you.
Thanks, Samya. Thanks for providing great opportunity at Women Who Code 2023. Yeah, let me get started. Today's topic is going to be on 5G security through threat modeling. Let me get into agenda. Agenda is first let's cover the preliminaries of 5G security architecture, then get into 5G network security architecture, then the logical entities for network access security in 5G, then 5G network access security procedures, and 5G network domain security. Yeah. So what are the challenges that we are seeing in the 5G today? Though there are major improvements in 5G, such as enhanced mobile broadband, ultra-reliable low-latency communication, massive mesh-type communication, there are huge improvements are provided as part of 5G, as part of enhanced mobile broadband. Now the data transfer goes in gigabytes per second. It provides 3D video, ultra-high UHD screens, and work and play in cloud, virtual reality, augmented reality, industrial automation, self-driving cars. These applications are close to ultra-reliable low-latency communication and massive messaging type communication, where we have smart city, smart home, mission-critical health, and voice. Voice are being provided by massive machine type communication. So there are various kinds of use cases and scenarios supported by the 5G. These are the improvements that have been provided as part of 5G. And also 5G provides more open, flexible, and programmable because of SDN and NFVs. In spite of providing this, there are a couple of security challenges associated with 5G, primarily on IoT devices, which are most attack types of hardware, and attackers have more access to personal data than ever, and SDN NFV opened up new avenue of security threats. So 5G must be architected to encounter these threats. Yeah, let me get into 5G architecture and reference point architecture. We have 5G service-based architecture and reference point architecture, whereas we have user equipment. This is the radio access network. This part belongs to the core network. So here, if you see, like each network function is connected via the physical interface, which are called N1, N2, N3, N4, N5, N6. There are dedicated interfaces are there for between the network functions in the reference point. This is till for 3G, 4G, 5G. There were dedicated interfaces were there between the network functions. But when it comes to 5G, we are like leveraging pub-sub model, publisher and subscriber model, wherein for example, network exposure function wants to talk to AMF. Network exposure function exposes the interface called NEF interface, and the AMF exposes NAMF interfaces. Whereas suppose if NEF wants to talk to AMF, first it will subscribe to the services that are provided by AMF. So as and when the AMF produces those messages, it gets notified, like NEF gets notified. This is how the 5G service-based architecture have been architecture. So if you see, this is the user equipment, this is the radio access network, this part is core network. Yeah, let me get into let me get into couple of network functions that are primarily used in security architecture. Though there were many other network equipments functions that are part of 5G core, but I am going to talk about few functions, network functions that are primarily used for the security. Yeah, the first function being AMF function, access and mobility management function. This is the part access and mobility management function. This is similar to MME, mobility management function in LTE, or VLR in GSM, which is similar to VLR in GSM. The functionalities that are provided by AMF are which manages UE registration and initiates authentication and provides mobility management. What is UE registration? When the first time the mobile is being powered on, it has to register with the network. So for that registration, AMF would provide assistance for the registration. Then it does the authentication. So the user equipments wants to authenticate with the network, whether the particular network is a legitimate network or not. Similarly, the network also authenticates itself with user, whether the user being a legitimate user or not. Right? This authentication is being handled by again AMF. And then mobility, another functionality provided by AMF is mobility management. So mobility management, the mobile travels from one region to other region. First, it might be in particular cell. Then the couple of cells are grouped together as a tracking area. The mobile can move from between these cells actually within the tracking area, and it can go across the tracking area. All these like cell IDs, this tracking area IDs are managed by the AMF. So these are the functionalities that are provided by AMF. Let me come to UDM, Unified Data Management. Yeah, this unified data management is similar to HSS in LTE and HLR in GSM. The functionalities provided, provided are access authorization, and it also tracks the AMF of, the user keeps moving from one location to other location. So each location will have its own AMF. So that tracking AMF of UE also maintained by UDM. And there are various security keys are stored in the UDM. And also the UDM is Unified Data Management. That UDM also stores the subscriber information such as data network US profile, access restrictions, mobility permissions, and roaming restrictions. So quite huge amount of data is stored in the UE is stored in the UDM. Let me come to authentication server function. So here we have seen like how authentication happens, right? When the mobile has to authenticate itself with the network. Similarly, network has to authenticate itself with the mobile. So for that, this authentication server function is used. Actually, basically when mobile sends its identifier to AMF to AUSF, from AUSF, AUSF tries to fetch the authentication vector from basically the subscriber's information from the UDM, and it passes on to the AMF, and AMF challenges the UE with a random number, and also it checks if authentication response is valid or not. So these are the functionalities that are being provided by AUSF. Let me get into NRF. NRF is the network repository function. Here, as you see, like there are various network functions. Each function profiles are maintained by the network repository function. This and also, so for example, this network slicing function wants to talk to AMF. First, it fetches AMF details via NRF, because all these profile informations and discovery is done by NRF. So it fetches the AMF information such as like IP address, domain name servers from NRF and passes on to network slicing function. So currently we have seen 4 functionalities. These are primarily being used for the security. So let us look at the preliminaries that are needed for 5G security architecture. So the first one being the 5G UE identifiers. The network 5G as a part of 5G UE identifiers, we have mobile terminal and the SIM. The each mobile terminal is being identified with the permanent equipment identity PEI or the international mobile equipment identifier. It's another identifier that is being used to identify the terminal. That to identify the SIM in 5G, the subscription permanent identifier is used, which is in fact, which is in C in 5G 5G in 5G. It is 3G for the 3GPP standard. IMSI is used for non-3GPP cases. Network access identifier is used. This is the identifier. SUPI is the identifier to identify the SIM. The SUPI is not directly sent to the network as such, like without being encrypted. The SUPI is being encrypted using the encryption algorithm, using the public key encryption algorithm, and it is converted as a SUSI and sent over to the network for the authentication, registration, etc. So these are the permanent identifiers of the UE. And let's get into the temporary identifiers. When user moves from one location to other location, that SUPI is not going to be used, or the IMSI is not going to be used. There is another identifier, temporary mobile identifier is going to be used, which is assigned by the AMF, which we have seen, access mobility function, which is assigned by the AMF and which is unique to AMF region. When user equipment moves from one location to other location, for that location's visited AMF assigns this TIMSI to the SIM. Or and there is other identifier which is 5G GUTI, 5G global unique temporary identifier, which is also assigned by AMF. This identifier is used when AMF region of UE is unknown. So let us get into a couple of the algorithms and encryption algorithms that are used in the security. So let's take a case like the sender wants to send the message to the receiver. It takes the plain text message and then it is encrypted with the key, the key, same key being used between the sender and the receiver. Using the key and the plain text message, using the encryption algorithm, the messages gets encrypted and that encrypted message is sent over to the receiver. Using the same key, the receiver decrypts using decryption algorithm and gets back the plain text message. Similarly, like this is the symmetric key, the same key is being used between the sender and receiver. If we come to public key cryptography, there are two keys used, unlike a single key in the symmetric key cryptography. Two keys are used here. The sender takes the sender's public key and then plain text message using encryption algorithm. It sends the text is being encrypted, and using the private key, receiver's private key, using encryption algorithm, the message is being decrypted and get back the original message. This is what the public key cryptography is being done. So let me get into the hash function to generate the message digest. For longer messages, there are more computational power is needed to encrypt the message. So our goal is to have a fixed length instead of variable larger message. For that, this hash function is used. Using the hash function, the large message is being truncated and have a fixed messages. We are going to have a fixed message. This message is called digest actually. So this is the one-way function from the h of m. From this message, we cannot go back to the original message. Unlike here, so here the original messages have been encrypted, and we are getting back the original message. But in this case, it's the unidirectional. We cannot get back to the original message actually. Yeah, using digital signatures, which is similar to public key cryptography, but the sender sends the message like message M along with the encryption. Whatever the message is being encrypted, Along with that, the message original message also being sent to the receiver, and the receiver takes this encrypted messages and decrypts and compares that. Once it gets the decrypt messages is being decrypted, it gets the original message, and it checks like this original message which is being sent along with the encrypted message is the same, and then the message which we have got from the same, if both are same, then then it confirms that the message has come from the legitimate user. So when I come to the digital signature and signed message digest, here this is again similar to the like digital signatures, but additionally, see this large messages are being hashed, and we get the fixed message. That fixed message is being encrypted, and we get the encrypted message. The encrypted message is appended with the original message. Then using the sender's public key, the messages are being decrypted, and again it checks like see this message, the original message is being sent to the hash function. We get the message digest, which is similar to this the digest message, and then the decrypted message. If these two are equal, that means that receiver received the messages from the legitimate sender. So these are the couple of preliminaries that are used in 5G security. Now let's get into, so we have seen the 5G architecture and then preliminaries, and then now we look at the 5G security architecture. There are the 5 kinds of security architecture that are used in the 5G. So, with the time constraint, I'm going to cover only the first 2 one. The remaining 3 are simple ones. So let's focus on the first 2 security aspects as part of this talk. So if you see like there are like 5 security that are being available, like network access security, network domain security, user domain security, application domain security, and service-based architecture domain security. So network access security, which is like the one, if you can see, which goes from the terminal to access network to the serving network to the home network. So all the way from terminal to home network, the messages are being encrypted, right? So using the network access security, there are various algorithms and procedures have been used to do these functionalities. We will cover in the upcoming slides. So second part is network domain security, which is between the radio access network to the serving network to the home network. Okay. That is covered as part of network domain security. And user domain security, the third part, which is just between the SIM and the terminal. So so user may need a PIN to access the terminal when we enter the PIN on our terminal to unlock our terminal, right? So that's where the third one, user domain network, is being used. And fourth one being like between the terminal and the services, which is application domain security. So yeah, this is what the application domain is. The fifth one is between service-based architecture to between the serving network to home network. So the functionalities that are covered as part of the first network access security are mutual authentication, privacy features. It provides a ciphering and integrity protection of user traffic and signaling, and allows NAS authentication over 3GPP and non-3GPP access technologies. And between the like network domain security allows securely exchange data and protect against the attacks between the PLMN to different PLMN, basically between the serving network to home network. Okay, the service-based architecture domain security, which does network function registration, discovery, authorization aspects, and protection of service-based interfaces. These are being provided as part of the fifth domain security. Now let's look at logical entities that are being used for the network access security, the first security, which we were discussing in the previous slide. So the logical entities for the network access security, these are the logical entities that are being used, and AR so ARPF, which is Authentication Credential Repository and Processing Function, AUSF, which is Authentication Server Function, SEAF, Security Anchor Function, Subscriber Identifier Deconcealing Function. SIDF is the Subscriber Identifier. We will look at everything in detail. So SEAF, which is Security Anchor Function. This functionality is being provided by AMF only, which is responsible for handling authentication in serving network based on the information received from UE and AUSF. So let me cover the authentication server function, because this covers the visited network, and the same functionality is being covered by in the home network by AUSF. This is the logical entity which resides in AMF, but AUSF is the standalone network function in 5G architecture, which is responsible for handling authentication in home network based on the information received from UE and ARPF. So, yeah. What is ARPF? This is a authentication credential repository and processing function, which consists of subscribers' security credentials. Basically, which this as we have seen in the previous slide, which consists of all the keys that are being generated as part of the security key procedure, which has all the keys like ciphering key, integrity keys, master key, and there are a couple of keys that are involved for the encryption, authentication, confidentiality. Well, all the keys have been stored as part of this ARPF. This is part of UDM. There is no standard interface between the UDM and ARPF, but the functionality is being served from the UDM. Now let's come to the subscriber identifier and deconcealing function. Subscriber identifier deconcealing function is the service offered by, again, UDM in the home network. It is responsible for resolving SUPI to SUSI. So in the previous slide, we have seen like we have got the SUPI is the IMSI, which cannot be sent to the network as it is as a plain text message. It has to be encrypted. That using the encryption algorithm, the SUSI is being derived. The SUSI is the one which is sent over to the network. Now let's come to the network access security procedure. So there are a couple of, we have seen what are the equipments that are used for network access security. Now we will look at the couple of procedures that are being performed as part of the network access security procedure. So the first being like authentication sets up the keys for ciphering and integrity protection. So the authentication happens between the terminal to home 5G network using the 5G ARCA procedure, authentication and key agreement procedures, and EAP ARCA procedures. This is for non-3GPP standard. EAP ARCA procedures are performed for the authentication. For the ciphering, between the terminal to node radio access network and 5G, which is G node B. So the ciphering recommended for signaling and traffic, but for integrity, this is mandatory. Similarly, between the terminal to visited 5G, ciphering is recommended for signaling, and integrity is mandatory for signaling. So let's look at how this authentication is done. So first, the UE sends message consists of SUSI, which is the encrypted from the SUPI, or the 5G GOTI, which is sent via N1 interface. There is an interface between them just to the AMF via N1 interface. So the message is being sent from AMF. The authentication message that it sends to from AMF to AUSF. Authentication request is sent with the parameter SUSI, and serving network name. Serving network name consists of mobile network code and mobile country code and the network name. So which is sent to the AUSF, and then AUSF sends the authentication request to the UDM with the SUPI and serving network name. So once UDM receives, does the authentication method selection, it sends the response back to, the response would be in the same format, which would be in NUDM underscore UE authentication underscore response. Similarly, like here in AUSF UE authentication underscore response, messages would be sent, and UE gets authenticated with the network. Yeah. So let's look at now. This is how the authentication is being done. The key generation part we will see at the later point of time, how the key generations are being done. Now, how this SUPI, where the SIM consists of SUPI, which is converted as a SUSI, using this concealment and deconcealment of procedures. The SUSI is created by UE. SUSI is created by UE, and SUPI is obtained back from SUSI from the network using SIDF. That's where this SIDF functionality is specifically being there. So SUPI, SUPI consists of these many fields. SUPI type, which can be like for 3GPP case, it is a IMSI, or non 3GPP case, it is a NAI, and which consists, again, another field is mobile country code, mobile network code, mobile subscriber identification number. So these are the fields that are part of SUPI, and these fields like MISN and using the home network public key, this encryption takes place, and it provides concealed user ID. And then from public key, we obtain the home key, concealed user ID. From the scheme ID also, from as part of this encryption, then we would be obtaining the scheme ID, and then routing indicator, and this mobile country code, mobile network being converted as the home network ID, and then SUPI type sent as it is. So this is SUPI. This is how SUPI is being converted as SUSI. Okay, by UE. Once this SUSI is received by the network, and then using the private key, home network private key, from these fields, we will be obtaining back the MIS, mobile subscriber identification number, and then MCC and MNC, we will obtain back the SUPI. So this is how the concealment and deconcealment of SUPI is being done. Yeah, yeah. This is what if GUTI is known, instead of SUPI, the GUTI would be sent over the network. Now let's look at the ACA procedure, 5G ACA procedure. Key ACA means key authentication and key authentication and key agreement procedure. How it's being done? Let's take a look at it. So UDM, Unified Data Manager, sends the 5G home environment authentication vector to AUSF, so authentication server function, with the parameters authentication random number, XRES, and K AUSF. So how these keys are being generated, let's take a look at it. So this UDM uses a millenage function to derive MAC, XRES, CK ciphering key, authentication key, and ciphering key, integration key, and authentication key by using SPN number, sequence number, and random number, AMF number, and key. There are using the millenage function. There are 5 sub-functions being generated. These functions provides MAC, XRES, cipher key, integrated key, and authentication key are being obtained from this millenage function. So authentication key would be obtained with the sequence number with exclusive OR of AK AK, and it is concatenated with the AMF key, and further being concatenated with MAC. Yeah, that's how the authentication key is obtained. So random number is, yeah, just a random number would be sent along with that. But how XRES is being calculated, let's take a look at it. So here we received XRES, but here we are sending XRES star. So here we are using XRES star. So the AUSF is the one which computes uh, star, HREX star, and store the XRES star within itself. So how HREX star is being calculated? So with the random number, the XRES which we have obtained from that is being sent as an input to the SHA-256 algorithm key derivation function. Then we obtain HREX star. So this is where the HREX star is obtained. So we know authentication number, we know XRES number, and the random number is with the just sent. Now we will take a look at how that KUSF key is being generated. Yeah, UDM derives KUSF key by taking the input like CK key, IK key, ciphering key, and integration key, and then the fixed number, and P0 is the serving network name and length of the serving network name, and P1 being SKN XR with AK, and length of SKN XR with AK. So these are being sent as an input using the key derivation function KUSF being calculated. So we now we know all the parameters how it is obtained. So AUSF takes those and computes HREX and stores XRES within itself and sends authentication random and HREX to the AMF. And the AMF stores this HREX within itself and sends only the random and authentication number to mobile equipment. From the mobile equipment terminal sends to SIM random number and authentication number, and this random number, by using this random number authentication number, SIM derives this CK key, IK key, and REST key. The way these keys are derived, similarly this USIM also derives these keys, and it sends to terminal, and terminal calculates the REST star key and derives further like authentication KUSF keys, KSEF. Similarly, KSEF keys are obtained from the fixed length, and then P0 being serving network name and length of the serving network name using the key and using the key derivation function. This KSEF is obtained. So the terminal sends the REST star and MAC to AMF, and AMF calculates HRES star from REST star. And compare it with already AMF stored HRES star, it compares itself with the HRES star. So both are matching, then sends the only REST star to AUSF, which we have seen already. AUSF stored REST star. So both would be compared, and it generates KSEAF keys. So this is how all the keys have been generated, and using the public key encryption algorithm, these keys are being used for the for ciphering and the encryptions. So now we will look at the 5G key hierarchy. The same thing how we have seen in the previous slide. So UDM using the key, it generates CK key, IK key. Using the CK key, IK key, it is KUSF keys are generated. From KUSF, KSEAF keys are generated, and from KSEAF, see the same hierarchy, like AUSF keys are generated. From there, KSEAF keys are generated. From there, KAMF keys are generated. From KAMF keys, NAS integration and NAS encryption keys are generated. It also generates the G node B key as well. From the G node B keys, RRC integration, RRC encryption keys are generated. Similarly, like user plane encryption, user plane authentication, user encryption, user plane integrity keys are being generated. So this is of the 5G key security key hierarchy being generated. So this is for the 5G 3GPP standard. For non-3GPP standard, additionally, for N3IW key is generated apart from the other keys. Mm. So now we have seen how all the keys are being generated, how authentication is being done. So this is what we have seen till now, how network access security is being done using the various keys and procedures. Now we will take a look at network domain security. Here, the network domain authentication, as part of a network domain security, authentication is implemented using IKE v2, which is Internet Key Exchange version 2, using digital certificate. There, from the network access security, we have seen using 5G ACA procedures, the key have been generated, and public cryptographic encryption have been used. But here, IKE is used for the authentication, and ciphering and integrity protection are also implemented using IPsec here. So these are the backcalls. So the terminal is connected to the G node B distributed unit to centralized unit, from centralized unit to 5G core network, 5G core network to home network, visited core network to home network. So all these authentications are based out of IKE v2, and ciphering and integrity, or again with ciphering integrity are mandatory for signaling and mandatory for signaling. Integrity also mandatory for signaling, optional for traffic. Here both are optional. Here the ciphering, mandatory for sensitive signaling and mandatory for signaling. So IPsec association. So how IPsec association happens? Suppose that the sender wants to send the message across the network to the receiver. First, it establishes the logical connection between the sender and receiver with the negotiating couple of parameters, and this logical connection is the unidirectional. If you want bidirectional, the two connections are being created actually. So when the sender has these details like origin interface, destination interfaces, and type of the encryption that are being used, encryption keys, and types of integrity checks that are these are stored with this, and it will negotiate with the receiver, and the logical connection is being established. So let us look at the IP framework. There is a Diffie-Hellman DH1 is being used, and for authentication it can be a PSK or RSA. For integrity, MD5 algorithm or SHA algorithms are being used, and for confidentiality we can select sender can select sender and receiver can select any of these options. Similarly, for IP protocol, authentication header, encapsulated security payload, these are the choices that are available before this logical connection being established, and sender receiver can choose what they want, which algorithm, which integrity type they want, which authentication they want to use, or which confidentiality they want to. They will negotiate and form this logical connection. So what are the services that are being provided by IPsec? It prevents unauthorized access control, prevents unauthorized use of resources and services, and it verifies the source of the security packets using data origin authentication, and integrity protection ensures that the receiver can detect if the that I mean the sender sends the data to receiver, whether in between the message has been altered or duplicated. All these functionalities are being provided by IPsec services. So integrity protection, detection and rejection of replays, and confidentiality. Now let us look at the types of IKE. IKE V1, there are two types of versions, IKE V1 and IKE V2. IKE V1 uses less bandwidth, IKE V2 uses more bandwidth, and because it's being built with a NAT traversal, and it also built with keep alive mechanism. So NAT is like something like uh, some a company has a lot of routers which has the private IP address which wants to talk to the public internet. There the public IP address is being used. So the NAT is the one which converts the public to the which helps in connecting public to private routers. Yeah. Mm. So IK phase one. So two peers again, as I mentioned, the two peers will negotiate which encryption they want to use, which integrity they want to use, and the lifetime of tunnel also, how long this tunnel can be up and running, and which Diffie-Hellman exchange algorithm can be used. That also, all these things would be negotiated and it authenticate each other. Then the tunnel is being formed. Similarly, for this is the IKE phase one. IKE phase two is used to protect our user data. This is mainly used for management traffic. This IKE phase two is used for the um, user data. Mm. So we use this IKE phase two. Again, this how that negotiation happens, what protocol it wants to use. This negotiation part is explained here. Um, yeah, now let's look at the encapsulating security payload protocol. This is the most popular choice of two since it allows you to encrypt IP traffic. We can use traffic or tunnel mode. Let's look at both actually. This is the original packet. The original packet is being encrypted like in the transport mode. Uh, this encapsulating security protocol header is prepended with a header in between these two, in between IP header to TCP header, and and ESP trailer is appended with the data, and then from here to TCP header to ESP trailer is being encrypted, and this message is completely being authenticated. This authentication message is stored in the ESP authentication. So this is in the transport mode. But if you tunnel mode, we don't alter anything. Like as it is, full original packet is being taken, and the ESP header is being prepended, and ESP trailer is being appended. Then encryption is taken place between the IP header to trailer, and the messages is being authenticated. So so here like completely like the new header is being added. So this is including IP header in ESP. The complete message is being encrypted. So this is more safer than the transport mode. So 5G chooses this ESP mode. Mm. Yeah, this is what is explained here. Actually, 5G uses the like because this is more secure. ESP mode is the more secure way, and authentication header versus ESP only provides service message. Authentication provides only authentication and integrity, but ESP provides authentication, integrity, and encryption. So ESP is the more popular choice. I have come to the conclusion. So sorry, I took more time. Any questions?
Yeah, we have one question. How do the security risks of 5G compare to those presented by 3G and 4G?
Yeah, 5G gives a secure, fast service and more reliable than 4G due to better use of bandwidth and more connection points. And the 5G standards of users authentication and data encryption are superior than 4G and 3G.
Oh, thank you. So thank you for asking such a great question, and also I want to give a big thank you to Suhuna for your time today and your amazing talk. I want to thank everyone so much for joining this session and being a spectacular audience.
Thanks a lot for providing me opportunity.